Right. Oh, no, I know Bennett down from the breath. Okay. Are there you?
I'm just grabbing the chair.
Teasing you. I mean, it was making a lot of noise. Oh, I shouldn't try this. All these little
As a graduate student, if you're doing that.
All right. So last time we didn't get all the way through the first lecture. Probably. Trying to follow Dr. Pitt's schedule. First time teaching the class, you're gonna have two options. Do what the last guy did and try and figure it out, or you can make it all up at the beginning. And when I taught fluids the first time, I made it all up. And that was exciting. And, it was like there's no net, you just jump. So this time I decided just want to follow his schedule. The problem is when you follow someone else's schedule, like you got to figure out the things they did, and you have to figure out the order they did it. It doesn't always make sense to you, the order they present things in. So as I'm like trying to figure it out, I add these little glue parts to sort of make it make sense to me. Sometimes that makes it take a little longer. Or there's other things I'm trying to figure out. How did he do this? Like a single lecture, like this is going to take me 3. So anyway, so hopefully we don't get too far behind. If we do, we'll cut out some stuff in the middle and we'll just go with it. So we can be a little flexible. We don't have like a bed breathing down our necks to tell us we have to accomplish X, Y, or Z. So if we get a little behind, don't worry too much. Okay, we can push back to homeworks or something if that happens, if we get to that point. So, I want to start with a prayer. Can I get a volunteer to start with a prayer? Is there anybody that would mind doing that? I'll volunteer.
Dear Holy Father, we're thankful for the opportunity that we have this morning to be your transport. And please bless that as we're here, that we may be inspired to be able to learn this material. And please bless Dr. ChEn, that he may be able to know how best to teach us. We ask for his name, Jesus Christ. Amen.
Amen.
Thanks, sorry, Doug. It's not a big deal.
That's it. The prayer is canceled. Okay. All right. I'm smiling. You can't tell, but that was a smile. I said I was going to do this. I assume you guys can still hear me. But do we have anybody? Do you have anybody on Zoom today, Jimmy? No participants. We're just broadcasting it for fun.
Yeah.
Want to get in the habit. Okay. All right. I can hear it if it's not okay. It's too loud in here. All right. So the last time, if you remember, so we were working right through lecture 1, and we talked about what is transport. We talked about the constitutive law, which was Newton's law of viscosity, in sort of elementary school form, yes, undergrad form or whatever, easy algebraic. Okay, he said it was we got Newton's law of viscosity to be how under x equal minus mu dvx dy, right? He said this was a relationship between this gradient here, which is a force, okay, and this was a flux of momentum, and we talked about that idea, and this introduces this viscosity, which is a coefficient, right, that's describing its proportionality, okay, how well is momentum transported by velocity gradients, okay, if this is high, a lot of momentum, right, gets transported really easily. If this is low, it's really hard to do that, okay, but this isn't very useful. Okay, it's only useful in 1D cases, and fluids flow in more than one dimension, and so we need to write a more general expression. And so if we say we're going to have something linear, and we have stress here, we can write in general fourth order tensors. Okay, And maybe those of you that took fluids with me maybe remember, but I'll just point out that for vectors and matrices and whatnot, I put lines underneath the variable. I think that's a really useful way of writing by hand. Okay, do that. So like often you'll see someone write a vector and they'll put a little arrow over it, one-headed or two-headed. Okay, in my notation, I put a line underneath it. Okay, if you have a matrix A, that's a matrix, I'll put 2 lines. Okay, meaning it's 2-dimensional. Okay, so something that's like a 4-dimensional matrix. Okay, it's kind of hard to recognize on that. Square, cube, and then I don't know, changing in time, whatever it is. Okay, 4-dimensional matrix. That's what you need most generally. Go from something over here that's a matrix. If you have, something to produce another matrix. Okay, if you're going to do that job. So that is a real pain for 3 dimensions. Okay, if this is 3D, and I have 3 to the 4 elements there. Right, that's 81 different elements, 81 different viscosity coefficients of some kind. Describe that. Okay. You don't really want that, right? So we can make some assumptions about that, about M. And so if we assume that it is isotropic, maybe something else. I think that's it. Okay, isotropic means that it's going to be invariant rotation. Okay, this actually goes from 81 down to 2. Okay. Really convenient, right? And this is the expression that we get out. I'm not going to do the math for it. I don't even think your book did all the math for it, but I'm sure you can find the derivation somewhere. If you're really interested, I can help you find it. Basically, it involves symmetry conditions. Okay, and you got these 2 coefficients. Okay, and so what you have here is the velocity gradient plus the transpose of the velocity gradient, okay, multiplied by some coefficient A, and minus sign in front of this one by convention in Burr's book. And then there's another coefficient B, okay, and this is the divergence of the velocity. And that's, now this is a matrix because we'll talk a little bit more about vectors and tensors and we'll kind of go over lectures, but for now, this is a matrix, this is a matrix, so we need to make this a matrix because this dot product is used as a scalar. So this here, delta, kind of looks like an H, that is the identity matrix. Okay, so that's the ones. So this one looks like 1, 0, 0, 0, 1, 0, 0, 0, 1. Like that. Okay, so this gets added in along the diagonal, right? And so what we have here are 2 pieces to this, and typically, A is our viscosity that we're used to, our dynamic viscosity, and B is equal to 2/3 mu minus some new viscosity coefficient that you've probably not seen before, which is called kappa. Okay, this is a dilational viscosity. Okay, also sometimes called a volume viscosity. All right. And if you think back to your fluid mechanics days, if you remember a little bit, what's going on here is that this guy is related to volume changes, okay, of our material, right? So for something that is incompressible, this is going to be 0. Okay, so when you think about incompressible fluids, that's going to go away, right? And we won't need that anymore. But for fluids that are changed in volume that have compressibility, you have to worry about the coefficient of viscosity. It has to be a change in volume. And what's essentially done, the reason there's this 2/3 here is this is subtracting out from this guy all the parts that have to do with the divergence. Okay, so when I take the gradient of velocity, part of there's a divergence down on the diagonals if I add them up. Okay, you can think of that as having the matrix as a trace. Okay, so the trace is the sum of the diagonal elements, so it's got a non-zero trace. And what they've done by defining this as 2/3 is you end up subtracting out the trace of this. Okay, so you see there's a minus sign there, there's a plus sign there. You can kind of go through and prove that to yourself if this is confusing. Okay, but you've got 2 of these matrices, so you do 2 of them, and then you do 1/3 of their that's where the futility is from. You can look at it in the book. So you could rewrite this if you want with the viscosity in here. It'll look like this: minus mu grad v plus grad v transpose minus 2/3 delta v delta, okay, and then minus kappa delta v delta. Okay, so if you wanted to pull out, yeah, go ahead.
Okay, so actually, I think you just answered. So kappa is 0 when it's not incompressible, not a whole second turn.
So if I have an incompressible fluid, this guy is 0. The divergence of the velocity is 0. So that will be 0. That will be 0. And maybe you remember this part of the expression. That's that before. Okay, so that's our more general expression. So the key takeaways are: you need to assume it's isotropic. You've got the nasty mess. Okay, and that gets you here. And then to remember the idea that there is these two coefficients: dynamic viscosity, which is the one you're happy and familiar with, and the volume viscosity or the dilatational viscosity. That's the expansion and contraction. Okay. Yes.
What is this del and v raised to power?
It's so it's transposed. So
Oh, transpose.
it's transposed. Yeah, so it's like in the book, I think they use a diamond instead of a T. So is it a T in the book? Either way. So in matrix notation, right? You know, if I have an A matrix, let's say 1, 2, 3, 4, right? A transpose is 1, 3, 2, 4. Okay. And sometimes people will use a diamond instead of a transpose. Normally they use this when they have complex matrices. So this would mean a transpose, and then if I have like a 2i, would be a negative 2i. So it goes this way. So anyway, I don't think we have too many complex numbers in this class. All right. Some fun stuff. Okay. So it turns out that how the stress we just wrote down. This is the momentum flux due to viscous stress. Okay, so that kind of makes sense. We talk about viscosity, so that's due to, shearing and stuff. Okay, but we can also have pressure that acts on the fluid. So if we want to add in pressure, okay, we get this new tensor, which is P delta plus tau. Okay, so now I add in the pressure. The pressure is isotropic, so it comes from all directions, okay, and it's always normal, right? So in a stress like this, okay, and tau, there can be shear stresses, right? So I can have, this surface here, I can be shearing this way, or I can be shearing this way, or I can have a normal force. Okay, the normal forces are on the diagonal. The pressure is always normal. You can't have shear pressures, doesn't make any sense to do that. Okay, so pressures get added on the diagonal. Right? And so this tensor here is called in first year in Lightfoot the molecular stress tensor. Okay, I think in my fluids class I called it the total stress tensor. What's going on here is that what they're saying is this is the stress that comes from all the molecules in the fluid interacting, okay? And we're going to add on to this convective momentum flux, okay? So we can have momentum that gets by viscous stresses, pressure, and now we're going to add on to it what happens when we convect stuff into or out of a cell, okay? So let's start over here. All right, so if I have some box that I'm going to look at, and I want to look at the convection into that box. This box might have some, let me just, so, you know, I might want to look in something like that, okay? So I'm going to just pick one plane to look at, and I'm going to say the outward normal is in that direction, so it might be that outer face over there, okay? And the velocity might be, you know, some other vector, so that would be from the plane. So N, that's the unit normal, the surface unit normal. Okay, and V is just the velocity. All right, so if I was thinking about, say, a mass flow, just that this is just sort of give us some motivation. So if I had just a mass flow, you might recall that it's rho times the volumetric flow rate, right? So that's just a mass flow into something. I can rewrite that as rho V dot N times the area. Okay, so the volumetric flow rate, if you remember, you know, we often talk about like a velocity times an area, but here I want to take into account the directionality as I'm going through this box. So I'm going to make velocity a vector, and I'm going to make the normal vector a vector, okay? So when I'm looking at this plane then, and what's the flow rate through that surface, I'm going to take the dot product, and that's going to give me the velocity in the direction of that surface. Okay, so I have some velocity coming there, and I only want to know the velocity in that surface in that dot product. Okay, so analogously, I can look at momentum flow. Oops, say flow. Finish writing momentum. Okay, momentum. So mass is just a scalar that's going around. Momentum is a vector, right? So I'm going to say m dot e, which is rho qv. Okay, and so I'm going to do the same thing with the q here that I did in the mass flow. I'm going to call this rho v dot n a. Okay, so a momentum flow through that area is, you know, this term, rho vv, dot with the surface normal, okay? And then we're interested in a flux. So a flux is a flow per area, all right? So this part is just the flux part, right there, okay? Hard to divide that when you're talking about it, just sort of can't do something to divide, you just have to pull it out, okay? So our momentum flux, okay, that's I guess our convective momentum flux. Convective momentum flux is rho v v. Okay, so that's the momentum per time per area. So momentum per time per area. Okay. So if we come back over here and we want to say what's our total flux, you probably just keep going down in your notes, but I don't want to erase it all, so I can keep the question. Now I can add them all up, and I can say, I'm going to define this new total momentum flux, which is going to be the sum of pi plus rho vv, okay? And that's going to be p delta plus tau plus rho v. Okay? And I think for word streamline, what they don't call this. They call this guy the combined moment impulse. They call that the combined. Okay. So what we've done, just sort of lay out a little bit of the math here, is we've tried to lay out, what are the mathematical expressions for momentum flow, okay? And we will use this to write our balance equations here in a couple of days. We're going to go through and do something similar for energy, and we're going to do something similar for mass flow, okay, for diffusion, and then we're going to sort of circle back around and go through all three again and look at the balance equation. Okay, so I want to stop here and make sure that we understand what's going on. It's a little bit, but just I think kind of writing this down and getting this in my head a little bit patient. I've breezed through the tensors and vectors. We'll pause and take a couple of days and do that here in a couple of days, but like I said, I'm following Phil's schedule. Maybe we could have done that before, but we'll remind ourselves and practice with those a little bit. But so if that's what you're nervous about, okay, we'll practice with that. So any questions? Yes,
It's a trivial question, but why do we use a little p for pressure instead of capital P?
I don't know.
Okay.
I don't think does he? I don't know. Does he use a big P? He uses a little P. Yeah, I don't think there's P. So we'll define a like a dynamic, or is it a curly P at some point, which is a P plus rho GH somewhere along the way. I'm sure. I don't know if he did that for that reason. I don't know if he uses a big P for anything else, but it has some kind of funky notation. That's one of the things about this book that's not my favorite. But. Okay, we good on this? Okay. I'll sleep yet early. I still have your attention. What's your class? You have one at 1 o'clock, right? 11. You have 11 and then 2? Oh, 3. 3. Oh, that's terrible. What's the one at 3? Kinetics? Is that Dr. Baxter? I never had him for like a real class. He was teaching us here. He was my brother's scoutmaster. So my dad is a professor here, and so when I was a kid, he did a sabbatical in Livermore, California, which is where I met Dr. Baxter. He was working at San Diego Labs there, and so we moved in, and he was the scoutmaster. My brother was 12, I was 14. And so I remember we went on some snow camp out with him. And he was always like this kind of funny dude. He tells these cowboy poems. And, we built snow, ice cubes, or whatever. And then when we came back to Utah after the sabbatical, Larry got a job here. So he like moved at the same time as us. And then when I was a freshman, because I knew him, he hired me to program for him. Like, I could program. And then I never really talked to him. I guess I had 391 from him. Anyway, didn't talk to him again. Really, we got hired. Just only having a full scope next week. Calling.
Until you got fired.
So I got fired.
You're not out of the program.
No, I went on a mission. So I worked for him for a year and then I went on a mission. So when I came back, I worked for Cowboy Filming, who's no longer here. He's retired. And I'll tell you the story sometime what happened with him. But I worked for him for a year, and then I worked for Randy Lewis for he had started, I think when I was on my mission. He moved from Oklahoma State. So it turned out my uncle was a professor at Oklahoma State, so they knew each other. So, all these professors. Family, like the family business. All right. My dad keeps bugging me, he wants to write a paper. So my little brother, I have a little brother who's a mechanical engineering student right now. And I have another brother who did an ME PhD and works here in North Carolina. My dad wants us to write a paper, tree. And that's the idea. He has no idea for what the paper should be. He knows the author line that he wants. So I'm like, can we just like go to Thanksgiving and not work? Like that would be nice, wouldn't it? We're in 3 different areas. My dad studies combustion, so he likes to watch the world burn. I'm theory and simulation of polymer materials scholar. My brother, who did a PhD, he did it on biofluid mechanics, so he studied hearts and blood flow and hearts. And then he went and got a job doing CFD, even though he did no CFD in his PhD, got a job doing computational fluid dynamics. My little brother, who's a sophomore this year, I don't know. He probably smart as one of us. You don't have a PhD yet. Yeah.
So what you're saying is you could burn polymers and see how they affect the heart.
So I thought I was like, there people do like they try and do pyrolysis of polymers as like a recycling back to monomers, try and get like various gases off. But that sounds so boring to study. No bash on anybody who does pyrolysis. That's not my thing. Okay, so we're going to do, stop that. Okay, so we're going to talk about the same thing we kind of just did. We're going to do the energy constituent law. We're going to do a little thought experiment. Familiar? Okay, and then we're going to do the general expression. And that too fast. My writing's bugging you, please don't slow down and write better. And then in 2, we'll do the total energy flux. All right, and then 3, if we get through today, we will talk about viscosity and thermal conductivity. Okay. Okay, so just like we needed a relationship between forces that are driving fluid around and how that leads to momentum flow, we want one of these for energy. Okay, remember that the conjugate variable to energy is temperature, so we're going to look for something that relates temperature gradients to energy flows. And so the thought experiment here looks really familiar to the one we showed last time. We're going to have 2 parallel plates. Okay. These are at 2 different temperatures. And at time 0, we will turn on the temperature. Okay. So this will be T0 here and T1. At time 0, we will turn on the temperature. And as we look across here, this will be T1. I'll have another number here, which is T2, which is a long time after T1. Okay, and again, if this is T0, T1, we'll put that just for reference. We get something that looks like that sometime later. Okay, so we start to have temperature conduct into that area. And this last one over here, T0, T1. And sometime later, we now have that T1. We have linear gradient. Okay, and we've got energy, energy flux from the bottom plate that's the high temperature to a low temperature plate above. Okay, And so you can think about, well, what's the heat flow through here? Okay, and you can measure the heat flow, and you find that the heat per area is proportional to the temperature gradient, where this distance here is big Y. All right? So again, I said, how do we come up with this? Well, we can measure this and then make a postulate, okay, and that's what this is. Postulate from lots of measurements, you do it carefully, this appears to be the case, you do it enough times, you say, you think this is long, all right? Or you can go out trying to find this theoretically, and there's some non-equilibrium thermodynamics literature that talks about how these forces and fluxes are related by linear gradients, sort of like a Taylor expansion argument. And we're just talking about the experiment though here. So we use this to define a thermal conductivity. Okay. Okay. All right, there's the thermal conductivity. All right. So you can rewrite this just like we did for the momentum case. Yes.
But so we are still moving on.
The bottom plate is fixed. What's different here is it's at a higher temperature. So this one is at T1. This one's at T0. So it's fixed. There's no velocity. Okay, we're just holding it at that temperature. Does that make sense? So there's a medium in here. It could be a fluid. It could be a gas. It could be a solid. And we're just heating this up. Probably if you wanted it to be a fluid, you want to do it upside down. So it doesn't off on the bottom, full on the top, a little bit of instability. That's not the way it is, right? So, okay, we can rewrite this as heat flux, little qy is equal to minus k dt y. So now this is a heat flux. You want to do that with pump heat flux in the y direction. Okay, so I forgot to put the little x and y axes, but they're the same as last time. This one's x, this one's y. So we've got heat flowing in the y direction, right, from the bottom to the top. Okay, and that's related to the temperature gradient in the y direction. That makes it a little different than the last case, right? In the fluids case, we had momentum flux in the y direction, but we had the gradient that had to do a Vx in the y, right? So that's what makes it complicated is that there's, in the fluids case, you have x, y, z of the momentum of the fluid, right? And then you have the gradient direction, right? And so, there's both of those you can count. And here, we only have a vector, okay? Because temperature is a scalar, so we only have temperature gradients in y. You don't have to worry about if there's a y temperature, Ty or T0, right? There's just the temperature. So it makes it really easy then to do step B, which is a general expression. Okay, for and this is called Fourier's law. I didn't say that. This one is Fourier's law. French dude, also French dudes in transport, makes it kind of fun. I went on a mission in France, so fun. So to write the general expression, you can just write down the full vector form here, minus k, it's not rad t. Okay? Okay, so it's the minus the gradient of the temperature gives us the vector. All right? Now, if we wanted something, this is also assumes isotropic. Okay? If we want something anisotropic, then we need a second order juicer here. So that will be Q, and I think they have a kappa in the book. What they call it. Okay? And I think there needs to be dot. Am I right about the dot? I think there's a dot. So we can look in the book. That's just what I remember from reading the book. Okay, so there we did 1 A and B. Any questions about the energy gonna say something else. I'm gonna put a C here. I'll write it. It's kind of an aside. So it's really useful to define rescale thermal conductivity, where we divide by the rho and the capacity, the density of capacity. This is the specific heat capacity. Okay, so it's per mass. Okay, so the mass density, right? And what's nice about this is that it has units of length squared per time. All right. And so we can also define other diffusivities. We'll see what a mass diffusivity, and we can also define a momentum diffusivity. If you recall the kinematic viscosity, okay, this also has units of length squared per time. Okay, and we'll see when we do the math that these diffusivities will occupy a similar place in our partial differential equations, so they end up meaning kind of the same thing, right? But this one is about thermal transport, and this, of course, is about momentum transport. So the other thing that we like to do in transport often, okay, if you don't know what to do, just make a dimensional number, okay? That's fun to do, get rid of units, all right? And so we can define here a Prandtl number, which is, I forget which one, it's nu over alpha, okay? And so this is the momentum diffusivity divided by the thermal diffusivity. And if you plug back in all the stuff, you get as mu Cp over K. Okay? And we'll just kind of leave that there, introduce Prandtl numbers now, or on this thing. Like a cliffhanger, you know, and then I'm sure you're watching. Just wait. Yeah, skip it. Okay? So I just want to make that quick aside about. Okay, total energy flux. Okay, so we want an expression for the total energy flux just like we have for the total momentum flux. So if you think about energy, there's the first law, right, which says delta U is equal to Q plus W, right? And this is the internal energy. This one is heat, and this one is work. All right? This one's for the closed system, right? So we can write the first law for an open system. We'll just do a little silly one. I call this M delta E is equal to Q dot plus W dot. Okay, so this will now be the heat per time and the work per time. Okay, this is the mass flow rate, and this will be internal energy that's being convected in and out. Okay, assuming that we have the same flow rate. So this is just help motivate our expression for doing it. You can imagine I have a box here. I have work. I have heat. I've got a mass flow rate. I have heat and heat out. And I've got the user related to this stuff. Does this make sense? Should be right for there. Yes.
Can you just go over real quick how you got from U to E one more time? Is it just?
Oh, it's this U.
This is okay.
Oh, no, this is here. That makes sense. Okay, so that's the idea here. So this is like, you know, first day of thermo kind of thing. This is like chemi thermo, right? Because we talk about stuff going in and out. Maybe I don't know. Mechanical engineers, you guys deal with open systems like this?
Yeah.
All engineers, man. Okay, I just don't know that, even though I have all these things in my family. All right. So what we're going to try and do, we know Q, right? So we know Q. We just found that out with Fourier's law. We like to find expressions for the work and then for the convective flux of energy. Okay, so let's do that real quick. So work, we'll do first. So for work, if you remember, work is something like force divided with the displacement. Okay? And we want, dw dt. Okay? So we're going to have force times d delta r dt, which is going to be force times the velocity. Okay? We're looking at something times force times velocity, so we can go back and think about our cube that we're going to invent force through. Okay? So we're going to have stuff like this. All right? And if I think about that one wall where I've got a normal vector here, and now I have a force. So I guess I'm not thinking about convection here, pardon me, I'm thinking about the force on some surface. Okay? I can write a force as the normal vector dotted with the stress. Okay? So the area of, so force is a stress times an area, but I want to take into account the fact that my surface could be in any orientation. So if I want to take that into account, I just have, the unit normal of my surface, dot that with the stress tensor, and that's how I get my force out. Okay? So if I want to know, I can take this expression and put it there. So I can say my work through time is equal to A and sigma dot V. Okay, and now this is my workflow, right? That's my workflow rate. So that's a flow. If I want a flux, I need to work per area. And so that's just going to be this part right there. So the work flux, we have they don't even give it an expression in the first written. It's just called the work flux vector equals sigma dot v. Okay? And they actually, so sigma is just some generic stress. In the book, they say, in particular, we're interested in the molecular stress tensors, they do pi dot v. Okay? So this one is just generic stress. Okay, this one is our molecular stress. Right, which is P delta plus half, if you recall. Okay? All right, so that work. Got work in. Let's do convection. Okay, so for convection, I want to look at these kind of terms, m dot e. Oh, and that's what I forgot here. So I drew this little guy, that asked me this question, right? He said, where did internal energy go? Okay, this can be internal energy, but it can also be kinetic energy, right? I don't remember what the right, I have an M out there, so I can do that. It can also be potential energy, right? Depending on how big the box is, right? If there's a difference in flow rate between and out. So I need to make sure that at least I don't do 1/2 v squared plus 2h. Okay? So that's the same thing we need to write up here. So for our energy flow, we're going to have m dot multiplied by 1/2 v squared plus internal energy plus, and in the book they use this phi, capital Phi hat, okay, for GH. It's just the same thing as GH. Like the worst. Okay, so in your book, in this part of the particular derivation where they're writing this out, I don't think they put this in, okay? They just neglect it, but then they sometimes put it in later, sometimes don't put it, okay? So it just matters whether height is important to the particular transport form, I think, whether they throw it in. So we'll sort of highlight that when we come to those problems. I'll make sure to put that out. Okay, so this, I said this is kinetic energy. This one's my internal. And this is potential energy. Okay, so now I can do the same game here that I've been doing with flows and fluxes, right? And I can say that m dollar E is equal to rho Q E is equal to rho E, and I said Q was V dot N A, okay? Right, so for any surface, right, again, with any unit normal, the flow rate through there is the velocity times the area. Just projected there, all right? And so this allows me to pull out the flux right there, okay, which is just rho EV. So the flux in a day is equal to 1/2. I put the rho back in, distribute the rho. Rho U hat plus rho U hat multiplied by velocity. Okay? So now I have Fourier's law. I have the work flux vector, and I have the convective flux vector, energy flux, convective energy flux. And I can put them all together and write a total energy flux. So all together, I get, and they give this the symbol little e. That's what they call it in the book. So it is equal to 1/2 rho v squared. Plus rho u hat plus rho v hat v plus that guy pi dot v plus q, which was my Fourier's law. Okay, and that's they call this the combined energy flux. Yes.
What's the difference between the V and kinetic energy that's not a vector versus the two other V's that are vectors? Okay, just a magnitude.
Yeah. Yeah, good question. Thanks for bringing that. Okay, so notice that the energy flux that adds a dimensionality to it, right? When we have a flux. So when we went from energy, which is a scalar, to a flux, now we have a vector. When we had momentum, which was a vector, we went to a flux, which was a tensor. All right, so we went up in one dimension. Okay, one more thing to say about this, and then we'll do 3D next time. So notice that I can rewrite this a little bit. If I pull the pressure I here. So if I just take these two terms, I take rho u hat v plus pi dot v. And I pull out the pressure out here. So this is rho u hat v plus p or p over rho. Did I miss something? Or did I do that? Just a p over rho. Oh, that's not yet. It's PV plus tau dot v. Okay, so all I did here was I expanded pi into p delta plus tau, but the delta and the dot makes it just go to a scalar multiplication. Right? If I have an identity matrix, it just the pressure's all coming out. Okay, now I'm going to pull out a rho. That's the stuff I was thinking. Okay, I pull out a rho here, and I have a u hat plus p over rho v plus tau dot v. Okay, and this I can rewrite as U hat plus P V. Okay, and that's an enthalpy. Okay, that equals enthalpy H. So instead of internal energy, if I want to pull out the pressure, I can have enthalpy. So I can rewrite this expression with an enthalpy instead. 1/2 rho V squared plus H plus, there should be a rho there, rho V. I'm running out of real estate. Now this should be a tau dot V plus V. Okay, so same thing, totally equivalent. It's just if you want to use enthalpies instead, okay, which is sometimes convenient in points. Okay, right. That's all I've got. Quick note on the homework. I took off a problem. So if you downloaded the sheet, just take a look. There was a problem from the last chapter and I took it off. So, yes.
On Learning Suite, it says it's due today.
It's
On your website, it says.
due next Wednesday.
Okay, cool.
Yeah, thanks for doing it. So, okay. Exciting. All right, that's all I got for you.